Okay, remember I'm recording. All right, so let's finish it up. All right, so groundwater. Dun, 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 we're finishing this up. Yay. All right, the easiest definition of what groundwater is, and to put it in layman's terms, is basically water in the ground. Okay, that's groundwater. It's just basically water under the ground. Okay, if you were to do it the scientific way, you would say that the water from precipitation seeps into the ground. Okay, it's kind of like when you water your plants and then the water disappears. Right? If you're watering the garden in your backyard and then the water just soaks into the ground, you're adding to the amount of groundwater that you have. Okay? How does it seep through? Through things that are called pores. Okay, just like the pores on your skin, there are pores in the ground. Okay? So the water is going to seep through the soil through things that are called pores. Through a process that is known as infiltration. Right? On that water cycle picture that I showed you, I said one of the words that you didn't really know yet was infiltration. Okay? This is the process in which water gets pulled down into the ground. Okay? This is the actual name of the process. Right? So you have condensation, which is when the water that's in the air goes down and condenses to a liquid, right? That's how you get dew, that's how you get fog, that's how you get a whole bunch of other stuff. Infiltration is the process in which the water gets pulled down into the ground. Okay? I'll give you guys another second. Depending on how big the pore space is, it's going to tell me how fast or slow the water will infiltrate through, right? So if you have something like different size sand versus soil versus, bless you, concrete, the water may or may not go through, or it's going to go through faster or slower. Okay, so let's talk about those factors. So what are the factors that are going to affect how well the water goes through the substance or not? Okay. First is going to be the slope or the gradient of the land itself. Right? If you have a very steep slope, if the water does not have time to infiltrate through. Right? So the steeper the slope, the less likely it's going to infiltrate it. Okay, if you have a nice low slope, right, then it has time to sit on top of the material and actually seep through. If you have it look like a roller coaster, right, it's going to be like you on a roller coaster, right? You're going to go flying all around. Right, and the water does not have time to actually seep through. Right? Degree of saturation, we've mentioned this a couple times before. How much can that piece of land hold? How much can that material hold water? Or how much water can it hold? Right? If you already have a saturated situation, right, it means that no more water can actually go through. Right? If it's already at its max capacity, then no more can actually be added. Does that make sense? Right? If it's an unsaturated solution or an unsaturated situation, right, that means more can be added. Right? Porosity, we're going to get into each of these a little bit better or a little bit more. Right? Porosity, permeability, capillarity. I believe that's the last one. Oh, and vegetation. Okay, we're going to go into all of these. Okay? These all are all the types of things. See, the problem is with weather and climate, guys, this chapter holds a whole ton of stuff. Or these two chapters, I should say, hold a whole ton of stuff. And the thing is, a lot of it is, okay, so here's the thing, and then here's all the factors that can affect it. And you have to look at each and every factor and say, do we have vegetation? Is it permeable or non-permeable? Is it porous or non-porous? Does it already have water in there? Does it not? So you have to look at each individual one, and that's what's tricky, right? And also, how is the land being used? That's what it means by land use. Is it farmland, or are we building an apartment building? Okay, so let's look. Or it could just shut off by itself. That's fun. Okay, so you have this thing called the zone of aeration versus the zone of saturation. Okay, the zone of aeration is the area in the ground. Both of these things, we're talking about the area in the ground. Okay, so the zone of aeration is where the water is going to seep through until it meets the zone of saturation. And we have a plastic water bottle on there, by chance? Like you can see through. Can I borrow it for 1 second? Thank you. Yeah, that'll work. Don't worry, I'll sanitize it after. Okay. Okay, when you're done, put your writing utensils down for a second. I don't have my actual water bottle, I have the other one. So. Okay, so we're gonna do it this way so you guys can all see it. All right, so let's pretend that the plastic bottle right here is the ground. Okay, I don't know if you guys can see it. Can you guys see how there's a little bit of air here and then the water's underneath it? Guys at home? Hello?
Yes.
Okay, so you guys can see that, right? All right. So, okay, I check your picture, because if they can see it, then it's got to be on you, okay? All right, so basically, if this is the top of the soil, right, and it's watering and watering and watering, this little area where there's just air is the zone of aeration. The area that there's water is the zone of saturation. The area or the space in between the two is known as the water table. Okay, so the zone of aeration would be on top, right, where this little piece of air is, right, because water can actually infiltrate through this. The bottom part where there's water is known as the zone of saturation. So how much is already there, right? And the space in between, that interface, is known as the water table. So the water table will actually rise and fall throughout how much water gets absorbed, basically, into the ground, right? So like I said, the water table is the zone, that interface in between the zone of aeration and the zone of saturation. So the zone of aeration is on top, and the zone of saturation is at the bottom. All three of these can increase and decrease it. Constantly, it's increasing and decreasing, I should say. Right? Because it's absorbing more, then that zone of saturation is going to increase, but the zone of aeration is going to get smaller. Right? All right. So you may be watching the news and they talk about the water table in the area. Or, I don't know, you guys have it as part of your project. For the climate part, you have to talk about the water table. Yes? Hopefully you guys started on that. Okay. So that can change. So if you'd like to take a picture of this, you may. Sure. So I downloaded the app for the project someone send me that. Like how do I use it? You put your data in and then it'll make the graph for you. Or you can use Google Sheets. You should be able to import it. Okay. Yeah. No problem. All right, so here we have, you can see at the top some graphs, right? In the zone of aeration, the space in between each of the particles does not have water there. Why? Because we can have more water come through. Then you have that blue line, which is the water table, and then you have the zone of saturation underneath the water table. So there's no real separation of them other than you have some soil, the water table line, and then zone of aeration, okay? And all of those pores in that zone of saturation have water in between them. Notice the two close-up pictures, right? In the zone of saturation, you can see the blue water, and in the zone of aeration, you can see how there isn't any. It's because at that point, it has gone through completely, right? This is just another picture showing the same kind of a thing, right? You have infiltration that is going down through the zone of aeration, and it will allow that zone of saturation to increase, okay? It's kind of where the water is being stored until things like plants or vegetation in general need it. And they use what's known as capillarity to actually pull the water up to feed themselves. That's why some plants and vegetation you do not need to water every single day. Okay? You might want to take a picture of this one. This one's a really good one. Okay?
Miss Gonzalez?
Yes?
It's Ethan. I just joined.
Okay, so I will just remind you at the end of the period, okay?
All right.
Okay, so the reason why this picture is so good is because at the bottom, you can see how it says the word impermeable bedrock. It means that nothing will go through. With permeability, it either does or it doesn't. There's no in between. It either does allow stuff to go through or it does not. So if it's impermeable, it means that the water will not penetrate through. Whereas if it's permeable rock or soil, it will allow it to go through. All right, picture. All right, so let's talk about porosity. All right, the typical definition for porosity is the percentage of total volume of rock or sediment that consists of pore spaces. So how big are the pores, basically, right? So you can see in this third picture here, right, the pores are very big. But in the second picture, the pores are very small because you have not only big rocks, but you have little tiny rocks there. So you have a heterogeneous mixture of large rocks and small rocks, which then basically cover up every little tiny space that there is, so it's less likely to move. So you would say that C is more porous than A or B. Okay, because it has bigger pores, which means that the water or whatever it is will move through faster. Okay, let's talk about how do we determine porosity. All right, you first have to determine it by the shape of the material that you're looking at. Okay, so is it perfectly spherical? Are they all perfectly spherical? Because if you have like a bunch of marbles that you put together, right, they're going to create equal amounts of space around them. But if you have pieces of marbles, right, they're going to kind of fill in those spaces, right? How they are packed together. Are they tightly packed together? Are they loosely packed together? Do you have a heterogeneous mixture? Do you have a homogeneous mixture? Do you guys remember those terms from last year? The prefixes hetero versus homo, right? You have heterozygous versus homozygous, right? Scientists use the prefixes over and over again, right? You have heterosexual versus a homosexual, the prefixes is what you want to actually think about, right? If it's hetero, it means different. If it's homo, it means the same, right? We're just looking at the prefixes. So as I'm saying, heterogeneous versus homogeneous, we are talking about different throughout versus the same throughout. So if you have a heterogeneous mixture, you have like this picture here, right? You see how if I took a sample from the top, the middle, and the bottom, I would get different shapes and sizes and probably different material? That is considered to be a heterogeneous mixture because it's different, okay? That's going to come into context with porosity, right? So the shape, how they are packed together. Are they tightly packed or are they just kind of thrown in? Sorting, is there a pattern or is it random? Okay, here's the big thing. The size of the material does not matter on porosity. Okay, you can have big marbles versus teeny tiny little marbles. It doesn't matter. The size does not matter for porosity. Okay, that's very important. Hence why you have 8 stars and 4 exclamation points. Okay. So, here's how you look at it. Now, if you guys can see this, some of you can, some of you can't. Don't worry about, for our meaning, you do not need to worry about the actual formula here. If you guys were in honors, then I would worry about it, or in college, if you take a class, they're going to ask you to actually determine the actual number for porosity. You will not need to for this class, okay? So here are the 3 things that we were just talking about. Packing. Are you tightly packed together or are you loosely packed together? Okay, that's going to have the difference between, if you're loosely packed together, your porosity is going to be high. If you're tightly packed together, notice the size of the pores, the holes in between each of them, right? The bigger the pores, the higher the porosity, right? You see when we said sorting, here we have they're both heterogeneous mixtures, right? This is a homogeneous mixture because they're the same throughout. If I took a sample at the top, the middle, and the bottom, they would be exactly the same, right? Even though these two are both heterogeneous mixtures, right? You notice how these tiny little marbles make the pores smaller. They get in between the bigger marbles, okay? And then the shape. If you have perfectly round material, they're going to make bigger pores than if you have more flat like discs. Does that make sense, guys? You okay with that? Okay. Let's talk about that permeability. All right? Permeability is a yes or a no. It's a does it or it does not. There's no in between. It either perms or it does not perm. Okay? So permeability is the ability to allow water or a liquid to freely flow through it. Okay? It could take an hour for 1 drop of water to go through the substance, but it's still considered to be permeable. Okay? So it either does or it does not. Porosity is going to determine how fast or slow that it does go through. But it's either permeable or impermeable. There's no in between. You can't sort of allow things to go through. Okay, so it either does or it does not. Okay, again, you guys are always welcome to take these pictures. Right? Here we have gravel on the left, right? It's well sorted, it has high porosity, right? And then the gravel sample on the right is a mix of gravel, sand, and clay. So that sand and clay is going to actually get in between the gravel particles, but they're both still permeable. Even though this has a low porosity, right? The holes are very tiny, right? It doesn't mean that water will not go through. Water will still go through both of them, Just one will go through faster than the other. You get that? Okay, so they're all pretty much permeable. Okay, capillarity. It's what we were talking about a few minutes ago with the picture of the flowers, right? Capillarity is actually, all right, it has to do with, all right, I'll give you guys a second to copy this down because I have to go cam on you for a second. Oh, really? Nice find. Okay, so you see how it says there's an attractive force between water and the surrounding material? Okay. They're talking about those intermolecular forces. All right. You remember how I told you that everything has an intermolecular force. It's just a matter of how weak or how strong it is, right? Water is one of those materials that, oh, maybe not. Okay. No. No, go back. Go back. You're ruining my presentation. I love when computers work. Okay, so water is one of those materials that, oh, fantastic. Okay. So what happens is it's one of those things that allows you to, it pretty much will do, okay, can I just have a blank screen? Thank you. Okay, it's one of the strongest intermolecular forces of attraction. It will actually break the bonds of something that is very strong. Okay, at all times when you have a water molecule, right, water is H2O, right? Are you going to let me? Yes, there we go. Right? Here we have a water molecule. I probably would. Okay. Water is going to have charges on it part of the time. Remember, I'm going all chem on you real quick. Okay. Those little D symbols stand for partially. So they're not fully positive and fully negative, but they do have these charges that happen. Okay? At all times. The reason why, you remember the picture I showed you where water was the pink elephant in the room, quote unquote, where water as a solid actually had more space in between than water as a liquid? Right? It did not follow the same typical formula, right? If I add another water molecule in here, because of course you are not going to have just one, right? There's always going to be an attraction between positives and negatives, right? That's that intermolecular force of attraction that I was telling you guys about. There's always a positive and a negative happening within the water molecules. So water is always looking to be attracted to something else. Okay? Because of those, just go positive, negative. There you go. Yeah, you just go one positive, one negative. Right? If I really wanted to do this, I can have this positive being attracted to this negative, this positive going all the way around this way. You know, if you really wanted to, you could. This is why when you have a graduated cylinder, if you look at it, you have to look at it and read it at eye level, because you can actually see water crawling up the side of the graduated cylinder, right? When you guys read a graduated cylinder, right, you have to get down on eye level because it almost does like this, right? That meniscus, right? You guys remember this? Did you guys have to do this last year? Right? You had to read undergraduate cylinder, so you actually have to get down at eye level and look at it. This is why. Because at all times, water is looking to be attracted to something. Okay? So it's constantly crawling up the sides. Right? Just think about that for a second. All right? That attraction is actually strong enough to rip apart some of the strongest bonds, like sodium chloride, table salt, right? It's one of the strongest bonds that you're going to hear about next year, and that's how you get salt water. Is it because it literally will rip it apart? Okay? Now, just keep that in mind, all right? Because capillarity and that water attraction is going to help to keep plants alive, right? Because if you have a small, tiny, tiny, tiny little pore, the water is going to climb up higher on either of the sides and pulling it all up, right? If you have a very large pore, okay, it's going to be, it won't climb up as high, even if it has the same amount of water in both of them, okay? So if it's a small pore, then water will climb up higher, and it's easier for plants to actually get to the water. Okay, so let's look at an example. Okay, I don't know if you guys can, oh yeah, you can, all right? Look how tiny this little pore is. You see how it's like a hole within a tube? Right? Look how tiny the pore is, and look how high up it climbs. They're all getting water from the exact same basin. So they all have the same amount or same access to the same amount of water. But if the pores are very, very, very large, right, it doesn't climb up as high. Now, if you look very, very, very carefully, you can actually see that meniscus. You can actually see the water on either side starting to like pipe up a little bit. Okay? Vegetation. Vegetation's fun. Vegetation are plants, animals, vegetables. No, it's just really plants. Okay? So this is going to have a direct relationship with infiltration. The more vegetation you have, the more infiltration you will have as well. Okay? This is why cities have a problem with flooding. Okay? Because cities, does anybody know what the Big Apple or New York City is also known as? You guys remember? You guys like the city that never sleeps? Called the concrete jungle. Oh, yeah. Okay? The city had a problem when it first was starting to be built up and everything because they didn't have enough of this. They didn't have enough greenery. Besides the fact that when you drive through the city, you're giving off pollution, right? And that carbon dioxide, if you don't have greenery, that doesn't be able to take that in and everything else. But then they also have a problem with flooding, okay? The more vegetation you have, the more water that can infiltrate through. If it can infiltrate through, that means there's less chances of flooding. Okay? There's less chances of flooding, it means that there's not as many problems. Okay? So let's look. This picture here, you have both, well, you have a couple things going on. You have the slope and gradient, right? You have the steeper slope and gradient on the right, right? And then on the left, you have vegetation and less of a slope, at least at the top part, right? There's going to be more infiltration if there's stuff in the way to let the water run off into the river, okay? So you're going to say, like, the vegetation stops it from running off, okay? It will actually grab those water molecules and pull them down, right? Versus on this right side, you're going to have less infiltration because it has nothing to stop it. It's just going to fly towards that stream. Okay? So the more vegetation you have, the more infiltration you will have. The less vegetation you have, the less infiltration you have. All right, so let's talk about land use. I said this is going to be the last one. All right? Humans are bad. I've been saying it the whole time. Humans are bad. If you take away that vegetation, if you just start making that industrial revolution, right, where you have more things, more big buildings, more things that are producing more pollution, okay, they're going to lead to less infiltration. The more buildings that you have, okay, the more concrete that you have. Concrete is impermeable. The water will never seep through the concrete. Okay? You're going to have less infiltration than you would in a nice foresty green area. Case in point, the next time it rains, I give you guys permission to go to the window. And I want you to look at, when you walk in, just go to the window, look at the parking lot versus looking at the little park that's right there. If you look at the parking lot, you will see puddles, right? You'll see usually little puddles. But this area right here, because it's at the bottom of the hill, floods constantly. Okay? I've been in this room for 12 years. I could tell you how many times that I've seen it flood. Pretty much any time it's pouring outside, it floods in this area. Okay? Versus if you look by the park where there's more greenery. Well, right now it's kind of brown, but more greenery, more vegetation. This is what happens when you do not have a ton of vegetation. Okay? I don't know why that truck thought it would be a good idea to try to go through it. But there are people, I noticed this last time I showed this, there are people with a canoe right here trying to come rescue the people who are over here. I honestly don't know if that person actually tried to drive through or if they got stuck, like a flash flood situation, but they were rescuing them, okay? We're done with weather! Yay! Okay, so what I want you guys to work on for homework are these practice problems, okay? Does anybody, I'll put this back up in 1 second, but does anybody have any questions?